is something called a priority queue. So what is a priority queue? So we'll think of objects having a priority. And this is often just a field called key. So think of you have a bunch of objects and they all have keys. And the key is the priority. So right now I'm specifying the abstract data type, which is I'm just giving a specification of what are the operations that you want to do. So you want to insert. You want to find the max, which means return object with the highest priority. So it's not, this is a very specific kind of find, right? You just want to find the maximum that's been inserted so far. Then you want to extract the max, which is delete the object with the highest priority. Okay, so I'll talk about the fourth one a little later, but these are the basic operations that you want to support. You want to insert, you want to find the maximum, and you want to extract the maximum. So a place where this comes up often is actually in your operating system or in servers, where like servers keep getting requests, right? They have jobs that they need to do, just like your CPU has like, various jobs to do. So every job comes with a priority, and the CPU has to decide which is the first thing to run and picks out the one with the highest priority, right? And it keeps doing that. Does that make sense? So when it gets a bunch of jobs, sometimes the priority is just who came earliest. But sometimes maybe your computer has to do something immediately, and then that becomes higher priority. And a priority queue is used under the hood to decide or to quickly determine, which is the maximum. And then once the maximum has been processed, you kind of remove it. So you don't need to find in general. You just need to find the one at the highest priority. And so there's also an operation which is increase key, which is, I'll say, which, if this is confusing, just ignore it. But the idea is certain jobs, you may want to increase their priority. You want to make them more important because they've been hanging around for too long. So these are operations. Yes?
I just can't read what it says in the parentheses.
This one.
Yeah.
With pointer to object. Sorry. I would write in caps all the time, but it would just take too long. Okay, so with pointer to object, right? Okay, so we can implement these operations using linked lists and sorted arrays and the kinds of things that we know and love. So let's go ahead and let's write out our table as before. So we'll do data structure here. So we'll do insert, find max, extract max, and then increase key with a pointer. What I mean is that you want to increase the key for an object to which you have the pointer to. Okay.
Are we assuming the same thing with extraction? We find the max and then extract that pointer?
You could also do it that way. But we don't have a generic delete with pointer. What you're saying is if you had a generic delete with pointer, then you could do it. But this is specific to the maximum, so it makes life, in some sense, you can optimize things even more. Okay. So let's start with just doing it as a vanilla linked list. So if you do a vanilla linked list, you can insert in one. you can increase key with pointer in O of 1. You could even extract max with the pointer in theta of 1, but finding the maximum is going to take you linear time, right? Because you just go through the entire list and you find out where the maximum is. But once you, yes?
Are we assuming the linked lists are not sorted?
Yeah, in this case, it's an unsorted linked list.
Will that be another kind we're going to think about?
A sorted linked list?
Yeah.
You could, but typically when you want to sort things, then you usually use an array instead. Because otherwise, the benefit of sorting is usually that you can do binary search. But if you have a linked list that is sorted, you can't do binary search on it. Because you don't have pointers to various things. You could think of a sorted linked list, though. Yes. So suppose you did a sorted array. What's going to change now? By the key. Yes. Because you're, yeah, exactly. Yeah. Theta 1, right? Because you could sort it in decreasing order or increasing, whichever one, and you know it's at the ends. So you could just keep track of a single pointer. Does that make sense? Right? So find max is theta of 1. Yeah? So I'm assuming you extract with a pointer. So usually I should have sort of said that, like, assume that you have the pointer. So if you have a pointer, then so it's finding, that's the expensive part. Right. So sorted array, suppose you want to extract the maximum. Then what? Yeah, how much? Yes? Well, but if it's just sorted and the maximum is at the end, yeah? You can just decrement the size of an array, right? You're keeping track of how many elements you sort of just decrement it. And you could put null there or whatever, right? So this is also theta of 1. But as we discussed before, inserting into a sorted array is expensive because you have to shift everything, right? So this gives you theta of n. Also, if you change the value somewhere, then again you're going to have to shift things back and forth. Or probably just forth and not back, but you have to shift theta n. So again, we see this trade-off, where this is theta n, this is theta 1, and when this is theta n, this is theta 1. And so can you get the best of both worlds? And so essentially what a binary heap does is it gives you the best, okay, but it doesn't give you theta 1, it gives you theta log n, which is pretty small as we saw. So a binary heap does an insert in logarithmic time, does a find max in constant, does an extract max in logarithmic time, and does an increase key in logarithmic time. Right? So it gives you the smallest, well, okay, up to log n. Essentially, think of log n as almost like a constant, so small. So it gives you like optimum fast performance for all the operations. Okay? You could do it either way, but all of these would hold whether you're doing it doubly or singly. That's right. So that's why I've been a little imprecise here. So if it's doubly linked list, then you only need a pointer to that object. Whereas if it's a singly linked list, you need a pointer to the previous one. So when I say extract max, I'm assuming you have found the relevant pointers. But you can, when you do the find, you could imagine the find returns a pointer and the previous pointer. So, okay, is this clear? So this is what we want to achieve. And a binary heap is, it's a really cute data structure. It's a really clever data structure that gives you all of these. So this is the part that's, well, the first time I saw this, I was like, this is incredibly clever. So the thing is, a binary heap is an array of objects. So it's just stored as an array, but we interpret the array as a tree, as a binary tree. So even we're not going to store any pointers. There are no pointers, but we're going to think of the array as a tree. So here's how we do it. So here's the array. This is conventionally makes the coding a lot easier. Conventionally, this is empty, meaning that we're not going to store anything at A0. It's going to be inconvenient to store there. And so we have A1, A2, going all the way up to size. Right, so this is A size. So just like you have a sorted array and you can just keep track of the size, you have a size field over here. The way we will think about the tree is as follows. We'll imagine that A1 is the root of the tree. And A1 is going to have children, A2 and A3. And A2 has children A4, A5, A6, A7, so on and so forth. So I want to emphasize that these pointers don't exist anywhere, but we're just interpreting the array as a tree in this way. Yes? Yes. Yeah. Okay? Okay, question. What is the parent of AI? Is it A of the floor of I divided by 2? Is it A of I minus n divided by 2, n is the size? Or is it A of I minus 1 divided by 2? Take the floor. Okay? All right. So what is the parent of AI? These are the options. So I'll give you a minute. Okay, so what is the answer? Okay, good. Most of you see it's that. So this is really neat because when I interpret things this way, if I want to go from a node to its parent, I just take the index and halve it. Right? I don't have to follow any pointers. So I just manipulate the index to reach the parent and the children. Note that the children of a node, so if you look at it, instead of parent, I said children, what are the children of AI? What are the two children? Yes?
Double it for the left one, and then double it plus 1 for the right.
Exactly. So you double it, so 2 times I for the left, and 2 times I plus 1 for the right. Yes?
So would we be storing the max at the very top A1 or at one of those leaves?
We'll store it at the top. That way it's all one. Right. But we'll get there. So first is, note that all of the structure has nothing to do with the values. So I want to again emphasize there's a point of confusion for those who've seen binary search trees. Binary search trees say that everything in the left has a smaller key and everything in the right has a larger key. That is not true here. The tree structure here has nothing to do with the values. I simply interpret the array as a tree. But I'm not saying anything about the values, not yet. I will say something. But so far, none of this depends on the values of the tree itself. Okay, so with this picture, a few more questions. So let the root be at, by the way, actually before I get there, so now I think you would appreciate why you make A0 empty, because a lot of this indexing becomes easier. You can also make this start from 0, and it'll be 0, 1, 2, 3, 4, 5, 6. The indexing just becomes a little messier, but it will work. Okay, so let the root be at level 0. How many nodes at level L? Okay, so let's say at most. Is it 2 times L? Is it 2 to the L? Or is it 2 plus L? Right, so how many nodes at level L? Okay, so what is the answer? How many nodes? Exact. It's blue. It's 2 to the L, right? You can see it over here. This is again amoeba doubling, right? The bacteria is doubling, so every node has 2 children, so it starts at 2 to the 0 is 1, 2 to the 1, 2 to the 2, so on and so forth. Okay, next question. If the heap, which in this case is just the array, has n objects, what is the maximum depth or the level? Okay, so I'm saying suppose this heap has n objects in it. How many levels do you have to go down to basically get all the objects? Is it theta of 1, theta of log n, or theta of n? And now, when you come up with the answer, I'm also going to ask you, how did you come up with the answer? Right? So what is your logic for the answer? Okay, I'll give you a minute. Okay, so what is the answer? Yes? Why? Yes?
Because in a binary heap, to extract the max, you have to use log n for like the timing purposes.
Okay, that's a really clever roundabout answer. So, but that's because you, okay, I got caught there. Yes, that reasoning is correct, although I still haven't shown you why it's log n. So I want you to use what you know from what's here to answer, but yes, wow, okay, so that was clever. Yes?
It's kind of the reverse logic of the first question.
Okay, why?
Because it's like finding out the number of levels.
Almost, yes. So one way to argue this is, you know that the number of nodes at level L is like 2 to the L. So once you go to log n levels, you would have seen n nodes, right? So that is correct. There's an alternate way of arguing this by looking at the parents. Yeah?
Say that like if you start at the top, every time you go down one side, it cuts the number of nodes that you're going to look at in half. Because it like cuts off the left side of the tree to look at the right side.
That's true, but in some sense, it's still that is right. But it's not. There's a very precise and simple explanation you can get if you just look at the indices of the parents. So firstly, this logic that was said is absolutely right. You look at the previous question, you say, look, at level L, you have 2 to the L nodes. So once you go to log n levels, you would have seen n nodes in the tree, right? Exactly. Can you use this? Yes?
Well, if you start at the last node
Okay.
and you want to get back to the root, you just have to go to its parent, which is the size of the array divided by 2.
Mm-hmm.
That parent, which is the size, that is the first parent you got to divided by 2, and so you're just having the size every time until you get to 0.
Exactly, right? So if you look at this, how do you get to the parent? You have the index. So how many times do you have to do this to get to the root? It's just log n. Does that make sense? Every time you halve the index, you go to the parent. How many times do you have to halve to get to the root? The root is 1. Again, the logic is the same as it's n divided by 2 to the I is going to be equal to 1. Right? Exactly, right? So does this make sense, this logic? That's the number of halvings you need to do. So this like innocuous equation comes up over and over and over again in all of these algorithms, right? So I'll say it so many times that even if I don't ask this in the test, you will still remember. That's like the greatest achievement for an instructor, right? To make somebody know something even though it's not in the test. Does this logic make sense? So there are two ways of seeing this. Both are saying the same thing in slightly different ways. The max depth, you can argue it using the earlier question or the parent question. So let's first look at the argument using this question. So we're saying here's the array. So this we know we're not storing anything. If you look at the first level, that's 1 node. The next level, that's 2 nodes. The next level is 4 nodes. So on and so forth. So once you go up to, so this is level 1, level 2, level 3. Once you go up to log base 2n, that level, that's going to have n nodes in it. So in some sense, you cannot go up to log n levels. You have to go up to log n minus 1 levels, right? Because you would see n nodes if you do this. The other argument is start from the last node, which is an. So the parent is an over 2, whose parent is an over 4, so on and so forth. Right? And so when you go up I levels, your index is n over 2 to the I. So when I is equal to log base 2n, we reach the root. Okay? Sometimes you see this enough times and you get philosophical. Like there's like the log function is magical. The fact that all of this is even doable sometimes is amazing. But anyway, Maybe I've seen this way too many times. So that's my problem. Okay, so does this make sense? So this is where the running time of log n is going to come from the fact that the levels is going to be theta of log n. And so all the operations we're going to do are just going to go up and down the tree. But note that there are no pointers, there are just indices that will follow. Does this make sense? Okay. Okay, now, so far I haven't said anything about the values in the tree. But now I'm going to impose a constraint on the values, and this is called the binary heap invariant. So an invariant is something that should not vary, meaning that the invariant is a condition that will always hold in the heap. Okay, that's what an invariant is. So this data structure, the binary heap, has an invariant, and the invariant is the following. The key at the parent is at least the key at the child. So what this means is that for all I, this is for all indices I, ai dot key is a2i dot key, and ai dot key is a of 2i plus 1 dot key, right? Because these are the children. So at all nodes, this needs to happen. So unlike real life, parents dominate children. I say this as a parent, right? So parents always have larger keys. That's what it means to be a binary heap. So a binary heap is an array where this condition holds. Does that make sense? So this conditional, so there's, again, you don't even need to know anything about the pointers. The pointers are just the interpretation of how we will manipulate this array. The only condition that we will have is the following condition. This is not the binary search tree condition, which is different. I'll say it again. The binary search tree condition is different from this condition. So please don't confuse the two. The binary search tree invariant is another invariant. The binary heap invariant is what is given here. So just to draw an example of a heap. So, well, before I draw that example, let me ask another question. So which element has the maximum key? Is it a of 1? Is it a of n? Or is it a of n over 2? Which element has the maximum key, assuming that this invariant holds? Okay, what's the answer? Hopefully this is clear. It's A1. So because A1 is the root, which is the parent of the parent of the parent of the parent of any child or any node, and hence it has the maximum. Just to draw an example, so here is a heap. So note that this is not sorted. It doesn't seem to have any structure. But if you write it out as a heap, the root is 42. Its children are 25 and 3, whose children are 15, 4, 1, and 2. Note that the 15 here is more than the 3 there. So 15 is less than 25, so less than the parent, but it doesn't say anything about uncles or aunts, whichever way you want to interpret it, right? It doesn't say anything about the siblings of parents. It doesn't say anything about the order between siblings. In any level, if you look at the nodes in a level going across, it could be a very strange order. So it's not like a binary search. I say this again because this question comes. It's not like a binary search tree where you can read off the sorted order by doing a traversal. Here, you can find the sorted order. It's more complicated. So does this make sense? But what is easy is that the max is always at the root. So what this means is find max, theta 1. Just look at the root. Find, not extract. Extract is going to be harder. Does this make sense? Okay, good. So the way that a lot of these data structures work, these being sort of the more complex data structures, is you define an invariant. Using that invariant, find max becomes easy. But now insert and extract max will become, okay, so I'll write this down. So insert and extract max operations change the heap and potentially destroy the invariant. So we need to fix the heap to restore the invariant. Okay, so this conceptual way of looking at the data structure is very different from, let's say, stacks or linked lists or your other data structures, which are more simpler. Here, it's not just like how do you get the object into your data structure. Once you get it in, there's an invariant you need to maintain. And if you just insert or delete, you'll destroy the invariant. So then you need to come up with ways of fixing it efficiently. And that's where all the cleverness goes in. And that's where the person who came up with this had to sort of think about what are the operations we can do to fix the invariant. So just to give you an example, I only have 5 minutes left, so I just want to motivate what's going to happen. If you want to delete in an array, so we said, how do you delete in an array? But if you shift, you're going to pay linear time. We want to do it more quickly, right? Exactly, right? You could just swap with the last and then decrement the size. So let's go ahead and do that over here. Suppose we wanted to remove 42. We have to extract the maximum. We know where the maximum is. So we would simply swap with 2 and then decrement the size. So let's go ahead and do that. So if you look at what happens to the array, it's going to become 2, 25, 3, 15, 4, 1. Right? So I'll just say that we put 42 here, but then we decremented size. So you can imagine this has been sort of removed because you decremented the size pointer. So now your heap looks like this: 2, 25, 3, 15, 4, and 1. This is not, or rather, this doesn't satisfy the invariance any longer. The invariants are wrong at the head. Does this make sense? Right? So you've performed your operation now. You've removed the maximum, but the invariant is broken down. So now you need to perform a series of operations to fix the invariant. And if you can do that quickly enough, then that gives you your extract max. Does that make sense? Now, if you look at this picture, it'll kind of tell you what you should do. So who's the next maximum? 25. Note that it's always the case in a heap that the second maximum is one of the children of the root. So the second maximum is always going to be one of these. It's never going to be anywhere below that. And which is the maximum? Well, you just compare the two children, and you see which of those is larger. That's the new maximum. Right? So in this 20, so it could have been, instead of, there could also have been 30. That would still be a valid heap. Yes?
Is it guaranteed that the node that we're swapping with is always going to be smaller than the two children of the head?
Good question. So suppose in this case, actually, it will be, because you always swap with the last. And if you look at that last node, one of these is going to be its ancestor. So it'll always have a larger value. Yeah. Okay, so, but even if it wasn't, just for an argument's sake, if that number was actually larger than these two, then you're done. It's already a heap. Although it can never be the case. But so that number is going to swap with one of these. It's going to swap with the larger of 23 and 3. Right? I said that it could have been, this could have also have been 30 and be a valid heap. So it's one of those two nodes. So 2 looks at the children, looks at the larger one, swaps with it. Right? So what's going to happen is you'll get 25, 2, 3, 1, 15, and 4. Is this a heap now? No. Why? Because there's a problem with this node. But note that there is no problem anywhere else. There's a problem only at the 2. There cannot be a problem anywhere else, because initially the whole thing was a heap. You only created a problem at the root, which is by moving the 2 there. Now the 2 will swap with the 25, so there's no problem with the root, but there's a problem there. But then you just do this recursively. You just iterate. So now 2 will look at its children, see which is larger, and swap with that. And just keep doing that until it reaches its place. Right? So between 15 and 4, 15 is larger. And so 2 ends up here. There's 4, 3, and 1. And so now we have our heap. Pretty neat, huh? So you just have to keep swapping with children, and this can be done in logarithmic time. Yes?
Why don't you just push the empty bubble down?
Push the empty bubble down. So
Well, you shift the thing over by 1, right? So you remove the starting point over.
if I were to shift the empty one down, the thing is the empty one might end up somewhere in the middle of the heap. And so let's say this, okay, so if you look at this example, suppose this was empty.